Thanks everyone for showing up again. So actually it would be useful to have been in the first talk to follow this talk. So essentially what I want to do is to focus on two of the areas that I mentioned, on verification and robustness, not talk about privacy, and do a little bit of a deeper dive into some current work. One that I mentioned about models that prove their own work, and another work that I didn't talk about, which is how do you achieve robustness against distribution shifts. These are joint works. The first one is with these characters here. This is Noga, Or, and Guy. Okay, so it's something that I started to talk about in the morning, but I'll cover it a little bit more in depth because I think it's interesting. And as I said, usually you get a model and it has an accuracy overall, like 99%, say, but then comes in a particular input X, let's say the model generates an answer. So you can think of X as, I don't know, multiplying two numbers together if you like, and Y is the answer. And even though 99% of the time it's supposed to work, actually when numbers get larger, I don't know if you notice it, but it doesn't work. But let's say it works 99% of the time, you'd like it to work every time. And that's the question. Can you trust that the output is correct? If not, then maybe we shouldn't use it. Or alternatively, we could say, you know what, when you're correct, give me a proof, and then I know which time to trust it, which time not to trust it. And then the question is, what kind of a proof? What do we mean by a proof? And the way that we define a proof is essentially by this notion that we say from theoretical computer science. So in some sense, there'll be a meeting here of machine learning and CS theory, computer science theory, and in particular computational complexity, and this notion of a proof that we came up with is we call it self-proving models, and it's somewhere in the intersection of machine learning and theory. So it has aspects that are sort of tailored to the fact that we're talking about machine learning, but it has also a flavor of coming from interactive proof system, which is something that comes from complexity theory, from computer science theory. And the idea is this: there will be the model, the prover as before. There will be a verifier. So we think of every proof as an interactive process. So usually you think about proofs as something written in a book. You check the proof, you know, QED, the end. Here, the proof is going to actually, in some sense, we make the place of the reader, the one who's reading the proof, explicit as an algorithm. It's a verifier. And not only that, it's not that you just ship over a proof and then the verification algorithm reads it, but we would like to give a larger flexibility. So we'd like it to be able to be an interactive process where the questions and answers that are being, so question one, answer, question two, answer, and so forth. Why do we want to make this interactive process? It actually buys us generality so that we can prove more complicated things with this interactive process. What we lose is that at the end, when the verifying algorithm decides that this is a good proof, or so it accepts the fact that Y is the correct output for X, there is a probability of mistake, but you can make it extremely small, like exponentially small. So, which means essentially that in exponential time, you're never going to see a mistake. That's the same thing as saying that the proof is, the error is exponentially small. So it's not 100% verifiable in the sense of classical proof. There is an error. It's extremely small, but this allows you to prove more things. It allows these proofs sometimes to be more efficient, and it allows properties like zero knowledge and other things that you might want down the line. But we don't focus on those properties here. So in terms of what we want from this, those two things I talked about, but here's two more things that I want to highlight for the deep dive, and that is, okay, we want the proofs to be correct, so we don't want the verifier to make a mistake. So usually when in the interactive proof systems, in complexity world, we say, on one hand, we don't want to make mistakes, but on the other hand, we want what's called completeness. And that is, we want to make sure that the prover can actually prove all theorems. Let's say that the theorems are a certain class. The prover can prove, that's completeness, and the verifier will not accept incorrect proofs. However, since we're in the machine learning world, we know that these models can't always generate correct answers, and certainly not always prove them. So we're going to relax that requirement. So whereas standard machine learning accuracy says we want it to be correct over a distribution, over X, for most X, we're going to say that we not only want it to be correct, but we want the prover to be able to convince us for most x's. So for most x's, it should convince us, and I'll never be convinced of something incorrect. So we recognize the fact that these machine learning models might not be able to be complete. They can't prove everything. But when they do generate an answer, they should be able to provide a proof, and I won't accept an incorrect one. So that's the model. And just a little bit more detail. Oh, if you want to sort of really understand what's going on, there's a probability distribution over the inputs. Maybe it's random inputs, maybe it's some other distribution, but we fix it. And the guarantees that we provide are with respect to this distribution. And then there's the verifier, as we said, there's the prover, and it's going to be, in the work that we've done, we're considering a prover, which is like a transformer model, at least the classical one, which is a sequence-to-sequence generator. So a sequence comes in, let's say you think of it, and then another token is generated and goes back. There's a longer sequence, now it's the previous sequence with a token, another token is generated, and this is how you're generating the answers. You think of them as a token by token generation. And then, to formally define the self-provability, you have to put all these parameters in place, to talk about the fact that you're taking x's to come from some distribution, and the y is generated by the model on x, and the probability that the model convinces the verifier to accept should be greater than some parameter beta. Okay, so there's a lot of, to be detailed, you have to put all these parameters in place. And one thing that it tells you, oh, never mind, is what's our goal? Our goal is to learn a parameter, the parameters of the model, so to update the parameter weights, or to come up with a machine learning model that maximizes this probability, that the prover can actually come up with a convincing argument to the verifier. And here's just a description of the sequence-to-sequence issue, where you have a model, a sequence comes in, then a longer sequence come out, because it's the sequence appended a token. So the reason I'm giving you these details is because this tells us the idea for the algorithm. How are we going to train the prover to come up with proofs, not just with that his answers are correct, not just with the answers. And the idea is that really, if you think about this questions and answer between the prover and the verifier, that itself is also a sequence. Question, answer, question, answer, question, answer. And each one of these questions and answer might be a long string, which is composed of several tokens. But altogether, when you write it out, it's also a sequence, just in the same way that X was a sequence and Y was a sequence. And what we want now is to learn how to go from X, right, from the input, to, Y followed by this transcript of, actually pi here denotes the transcript, which is the output Y and the question and answers. And in fact, really what you want to learn is the answers, the red arrows, because the questions the verifier itself comes up with. And to train it, the idea to training it is essentially by optimizing toward generating accepting transcripts rather than non-accepting transcripts. And in order to be able to do that, we need to be able to sample X's and sample transcripts, which are accepting. And this seems a bit weird. We're using model to come up with answers, Y, and in order to train it, I need to have X's and Y's and transcripts. So the issue is, it's just like in machine learning, you see lots of examples, okay? Here the examples consist not only of the X and Y, but also the proof. So we have somehow access to a data set of transcripts that have convinced this verifier of the correctness of Y for X. So it's not a specific X, it's like a family of X's. Like if you think of X as a multiplication, so there's the pairs of numbers you're trying to multiply, and then there's the answer, and then there's a proof for it. Of course, you want this verifier to be cheap. To be cheap, I mean efficient. You want it to be faster than actually doing the multiplication itself, otherwise the whole point is worthless. And you do this by gradient descent. And then there's the theorem that I pointed out, which says that under some conditions, you can actually prove that this gradient descent method is going to work. And this is how many rounds, iterations for training that you would need to do. And I'm not going to look at all these parameters, but an interesting parameter is that the length of the proof. So the longer the proof is, the more iterations, which kind of makes sense because of the sequence-to-sequence nature. So if you can come up with laconic proofs, so the shorter the communication is between the prover and verifier, what you're expecting, the easier it's going to be to train a model that can come up with these proofs. And I said that we did some experiments. So let me skip over this. So there's also, you know, well, a very good question is, where do you get these transcripts from? And you can get them because you need access to a data set of these pies in order to be able to train the model. And you know, there's essentially a huge literature on these things, how to come up with doubly efficient interactive proofs. I'm not going to get into it. And another approach to this is reinforcement learning approach, where you actually learn from the verifier feedback. So in other words, you try to generate transcripts. Some of them get accepted, some of them don't. So essentially you just do sampling this way. So you only keep the accepted transcripts and then you use them. Okay, let me see whether it's not moving. Ah, yeah. So you're generating it, you take the ones that accept, and that builds your database of transcripts. And then you update your parameters toward accepting transcripts. So who is this? This is Euclid. So when you take computer science, introduction to algorithm, the first algorithm they tell you about is greatest common divisor. You have two numbers, and you want to find what is the largest integer that divides both of them. And this is an algorithm. To do it was developed by Euclid, Euclid's algorithm. And beautiful algorithm. There was a paper by Charlton in 2024 that showed a very small GPT built a transformer that computes greatest common divisor. But it didn't do it by running Euclid's algorithm, which we all know how to do. But it did it, you know, by training on examples. And he actually approves, I mean, with experiments, that you can compute the GCD and do quite well. However, he doesn't, at the end, you get an answer. Do you know it's correct or not? So our first set of experiments were, can you train a model to produce also a proof that the GCD is correct? Now, why choose GCD? First of all, there's some charm about GCD because it's the first algorithm ever. But the real reason for using GCD is because it turns out that if somebody tells you that the greatest common divisor is some number, okay, there is actually a short proof of that. And it so happens in mathematics, it's called the Bézout coefficients. Essentially, if you can find two coefficients, so this linear combination, like say these are the numbers you're trying to find the greatest common divisor. If you can find these two numbers, such as this plus that, so a linear combination of your x1 and x2 divides both x1 and x2, that's a proof. I won't get into it, but that proves that this is the greatest common divisor. Not only that it divides x1 and divides x2, but it's the largest such number. And that sort of gave us a goal. So our verifier was hoping to get these coefficients. So you remember there's a prover and there's a verifier. And let's say the task now is that the input is two numbers and the output is, here is the largest number that divides both numbers, what we call the greatest common divisor. And now you have to verify that it's the greatest. So what we wanted was to train the model to output the proof, which are these coefficients. Maybe that's a little bit too much. Anyway, so say, what is the GCD of 92 and 78? He says 2. So maybe yes, maybe not, maybe there's a larger one. Well, if it gives me these two numbers, I can essentially do the following check, which is check that in fact 2 divides this, both the first number, 92 and 78, and there is a linear combination equals 2, and that provides proof. Never mind, too many details. But the point is, really, what is the point? The point is that it seems to work. It seems to work. That is that this paper by Charlton, he got 99.8% correct computations of GCD. And we said, okay, but we want to do transcript learning. We also want a proof. Then we went down to 60%. So requiring a proof made it so much harder. But then we added something called annotations. So a few steps of Euclid's algorithm in the middle. And then we managed to go all the way up to 96%. An interesting question is whether by forcing these models to prove, whether you can make them actually be more accurate. Here it seems like you always go down. So you give an answer and then answer plus proof, that's harder. But it could be that this is actually going to make the algorithm better because it sort of teaches it. how to prove its own results. So it would be kind of an intermediate step. All right, so there is Euclid and annotations. Let's just skip that. But they asked me for a deep dive, so a technical talk, so it's technical. And there's related literature. It's interesting, there's a lot of literature now about proving. So there's Lean, there's math language for proving math results, a metamath. There's the use of proofs for safety and alignment. So this debate system where they sort of argue back and forth about what's correct in order to both prevent hallucinations, but also kind of is used for alignment, for interpretability, and so forth. So this whole idea that there's a proof in the process, and there's a verifier, and sometimes the verifier is like in our case that we bring it from the outside. Sometimes the verifier is learned by the system itself. It's a kind of an extensive area of research. What time is it? This is not the end. 5 minutes. Interesting. Well, they claim it's the end. There was something about robustness there. Can you check what happened to my slides? It's an autonomous, not vehicle, but autonomous decision that I've talked enough. No, that's the beginning. Okay, no, you're right. So I was going to talk about this other paper, and that's with Omar Montasari and Adam Kalai and Yael Kalai. And the question here is completely different. So we're not talking about verification anymore. So if you go to the way the machine learning definition by Valiant in the beginning, he was saying this. Learning is, and this is very early, we're talking in 1984. We've labeled examples for some function, x and f of x, okay? And now we see examples, and a machine learning system is successful, we call it pack learning, if it can generate an hypothesis, a model H, that agrees with the truth, with the ground truth, approximately and with high probability on inputs drawn from the distribution. So you want to learn something, an H, so that from now on you can use H, and the probability you're going to be wrong, that is disagree with F, is small. So the probability that the mistake, the probability that the error is small is high. It's the same way as saying that the probability you're going to be wrong is small. But why did I put the slide on? Because the whole theory was that you are training on distribution D, and then you are required to be successful on distribution D. So the train distribution and the test distribution were the same distribution. But that is just not the case. That's not what happens. So really what a way to see it is, suppose you just look at this very simple, you got a bunch of examples. There are plus examples, the greens, minus examples are the blues, and let's say what separates them is this function. And now a machine learning algorithm comes and they come up with a hypothesis H. It's pretty good, it separates the plus from the minuses. And when you get the test examples, you see that the ones that, if the distribution is the same as what the train is, this works well. But what happens when the test distribution changes over time? Can you have any guarantees? And what happens even if the test distribution is chosen by some adversary? He really wants to trick you. He knows what your model does. Now wants to do something different. Usually people talk about self-driving cars, right? So you're going to show the self-driving car some dangerous image, but they don't recognize it as dangerous, and they sort of, run into an accident. So that's what robustness is about usually. And then here's an example that I mentioned in the talk about in lungs before and after COVID. That's another distribution which is not adversarial, but there's still a major distribution shift in what you may have been trained on versus what you're tested on. So we have this result that shows you that even for adversarial distributions, you can do something. And it's very much counterintuitive, at least to me in the beginning. And what it requires is two relaxations. One relaxation is, first of all, we're going to allow our model to abstain. So if you think about high-risk cases, so let's say you are a surgeon and you're using the model to advise you whether to cut or not to cut, saying if what you see is very different than what you've been trained on, you say, halt, I don't know. And second exception is that we're saying, before you, part of the training is when you are, as you are using it in the field, you are, and this is an assumption, you are given a whole bunch of samples from the future distribution, okay? They're unlabeled, but at least it allows you to test whether the distribution you see and the distribution you are trained in are close or not close to each other. So when is that going to happen? When you're in the hospital in this example that I gave, that's obviously not applicable. You're not going to be able to get lots of samples of somebody who's like your patient. But let's say you are talking about recognizing bad content for YouTube. You know, so they get content all the time. Should they publish it, not publish it? They're not supposed to publish pornography and so forth. It's done automated. You could imagine that you would be looking at a whole bunch of samples from a user, and before you decide, you know, what is the model that will decide to accept or not accept from that user. This is on the assumption that this user always behaves the same, but can also be tailored to a situation where the user is adversarially changing individual inputs. Okay, in any case, that means that we have, why are we making these assumptions? Is it just because we're bad mathematicians and we don't know how to solve things? So no, it's impossible to do it otherwise. So if we think back about that original picture, where there were the pluses and the minuses, and then we had the test, which were these black dots. What if all the black dots are here? And we've never seen examples here. Our pluses were always here, our minuses were always here in the training distribution. All of a sudden, this is what I'm being tested on. There's absolutely no way that I can know whether it's a plus or a minus. So I don't know if the function really goes this way or that way, which would change the labeling. So I need to abstain on it. So that's why we're saying allowing abstaining, it seems you can't, there's absolutely no way to be correct. And in terms of seeing future, why did we need access to a whole bunch of test examples? That's really, again, it's because an adversarial tester could put his questions very, very close to the sort of decision boundary, and that would be very hard to tell unless I had examples of the test distribution. If I only had one, for example, rather than a whole bunch of unlabeled test examples. But what we show is that if this is the case, if you are allowed to abstain, and if you are, and if you are given extra examples from the test distribution, you can get fairly nice results. So for every training distribution P, for every test distribution Q, as long as you get enough examples, let's say the same number of examples for training as for the test, then you could learn an hypothesis in a region where in that region you should answer. If you're not in that region, you should say, I don't know, and you could prove some bounds on, you know, that your rate of abstaining with respect to P, which was the original distribution where you shouldn't abstain because you were trained on it with labels, plus the loss or the error that you would make on the test distribution, okay, whenever it does answer, is bounded. So that's the definition of what we want when we define this PQ learner, and then we can actually prove a theorem that you can get that. So I think there's the algorithm, but I won't bore you with that. And at this point, I will finish. This was really a deep dive. I apologize for all the technicality.
Thank you so much.
Thank you.
We have time for Q&A.
Oh, okay.
So we have around 3 to 4 minutes for questions.
You can ask me a question about my previous talk. Yeah. Any limitation on reinforcement learning? There's a limitation on any kind of learning, including reinforcement learning. But reinforcement learning is very, you know, important and highly studied. So,
would it be possible to teach an AI how to hack?
yes, absolutely. I mean, AI systems are very good at coding. The question is whether you want to make sure that your devices can avoid those attacks. But that's an example of a coding challenge.
Thank you.
We'll take another question.
I have a question from your previous talk.
Yeah.
I'm creeped out by the problems of AI, ChatGPT, etc. And so when I go on Google or whatever and I search, I can't figure out if what I'm seeing is true or not.
Right.
And it bothers me, so I'm a Luddite, and I ignore most of it. And so my question to you is very practical. Do you have any advice for me about how to do any research?
So you're creeped out also by Google search results?
No.
Oh, because you said Google. Okay. I wouldn't use it to make any decision that has consequence. If it gives you some psychological advice or tells you how to talk to your friends, use it by any means. It seems, but if it's something that has actually either, health consequences or financial consequences, I would definitely not use it. I would use it for rephrasing your text, for writing, I don't know, grant proposals or things of that nature. But that would be my advice at this point. When you don't have these assurances, like some kind of an argument, transparent argument and a way to validate, I think I wouldn't use it. That doesn't mean that there's not going to be tons of investment of hundreds of millions of dollars into industries that tell you to do just that. I just personally think that you could take it as advice, cautionary. Yeah.
Thank you.
Thank you so much for the questions. I'm afraid that we have 1 minute if you have any question.
Thank you. To what extent are these verification systems applicable to multiple different modeling types, say XGBoost and the like? And are there any libraries out there publicly available, open source, say, which we could look at and play with?
No, it's really the beginning. This is a paper that we just submitted. It's a first result. And there's certainly not verification systems out there that you can use. But there is work with people from the programming languages community to develop, more general purpose systems. And my guess is that down the line you will have verification. But you could sort of envision that there's going to be this world where there's these verified ground truth facts. And there will be a way to parse answers so that you could see whether they're grounded in these facts or whether you can derive a contradiction. And I think that that's work that has to be done. Probably this is the role of academia, because I don't know that, companies out there want to devote their resources to that when they can just sort of charge ahead. It's an interesting question, whether they would or they wouldn't.
Thank you.